laid out down here the memos that were submitted over the weekend. They've been graded. So this is Tuesday 12:30, 12:30, Tuesday at 3:30, Wednesday at 3, Thursday at 12:30, and Thursday at 3. You don't need to pick it up now, but before you leave, please come pick it up. Let me just make a few comments about memo writing, just in general. Let's just kind of recall what you're doing this semester with your memos. The first thing is to remember is that these are progress memos. Okay, and so the key word there is the word progress. What is the progress that you're making? And so it makes sense to say, well, this is what we're trying to do, and this is what was accomplished. And then let's get some evidence that that was done. And some figures of data, or some things that you've been collecting, say, with an oscilloscope or logic analyzer, have made sense. It's going to be increasingly more challenging as the semester goes along because you're going to get more and more data. And so you're going to be faced with the challenge of figuring out what is some of the evidence that's going to support the claims. Okay, so evidence to support the claim. So one of the things that you're going to say is, well, the GTA saw our stuff and it worked. That's a claim. Let's have some evidence to support the claims. And so it could be instrument screenshots. Okay, those are some of the common things that I saw. Logic analyzer, oscilloscope, those. But increasingly, you're maybe going to have to think about figures like graphs. You might have to create some tables of data because you're going to get more and more data, figures and tables of data, maybe to think about. But the key thing to think about is that this is progress. Okay, so what I saw in a lot of the memos this past weekend was a lot more than progress. It's great that you're all enthusiastic, but it's a lot more than progress. I saw a lot of what I would call technical details that are suitable for, say, a design review. Somebody wants to know, well, how did you do this? That's a technical problem. I'm not interested in so much in how did you do it, but how's the project working out for you? All right. So this is not the same thing as, say, a technical design report. Okay. So some of the memos tended to be probably a little bit longer than necessary. An example, a number of people attached a C program listing. They put 4 or 5 pages of the actual program. But whether the program works or not is not going to be telling me, attaching this thing doesn't tell me whether or not the program works. And so it doesn't really contribute to answering the question, what is the progress of your team overall? So it's probably not as appropriate in a progress report. Had this been an assignment where you had to explain in detail how things work, like a technical design report, then the C program listing might make sense. Okay, C program listing here is maybe not so useful. In a few weeks, you're going to have another type of assignment. It's what we call the experimentation report. Again, that is a different type of goal. It's different than progress. It's trying to communicate a different piece of information. But these are just some general suggestions. I think some of your memos could be more concise. They could be a lot shorter. And so think about that in future memos. Each of you has now written one memo. Each of the team members has written one memo. There was a person who wrote memo A1, and the teammate wrote memo B1. And then in a few more weeks, one of you is going to write your second memo, your last memo for the term. And then about a month from now, the teammate will write the last memo, his or her last memo for the term. Okay? We are now here this week. We are at week number 5. We're going to do this week what is known as the keypad controller. The keypad controller. There's some good news and some bad news. The good news is there's really no more technology that you have to learn to get this done this week. For example, last week you learned about the interrupt service routines, and from what I gathered, it seems like most people are getting the handle on that. You will need to learn how to use, to write to a port a digital value and read from a port a digital value, something that we did in weeks 2 and 3. So you're going to build on what you've already learned from weeks 2 and 3 to do this. So that's the good news. We're not going to learn a new module or anything like that. In fact, today's discussion, the presentation, doesn't talk about more flags to deal with and more unusual subsystems within the microcontroller. We're going to try to integrate some of these things that we've been working on for the last few weeks. That's the good news. The bad news is, historically, this has been the toughest assignment for the semester. And so many students will feel a little bit frustrated, maybe even want to think, I need to go drop the class because I didn't get the lab done this week. So my encouragement to you is don't feel that way. Many students don't get it working the first week, this week. And some students, some teams might take, they may not get it working to their personal satisfaction until the very end. That's okay. That's a little bit of real life. You have goals, you work on it, and it doesn't work out exactly when you think it's going to work. So if you don't get it working in week 5, don't sweat, okay? But I'm just warning you that it is one of the tougher ones historically. I don't know why. Dr. Nelson and I used to just shake our heads. He says, they learned the keypad controller in 2220. And I said, well, you computer guys, you just have tough things to learn, I guess. And then maybe it's the C programming or whatever. I haven't been able to put my finger on what it is, but it is maybe because it's a complexity of integrating so many ideas together that it is a little bit of a challenge. So there's some advice here that I would probably share. Again, because I don't know exactly what the problem is, I'm reluctant to say, well, you can solve it if you do this, because I may be off base on what the issue is. But really, I would try to have a draft program before lab. My pen's before lab. Okay. In some of these previous weeks, if you didn't have your program completely done and you're going to kind of design it a little bit while you're in lab because you want to explore some things, you can probably get by with that. But this week, because of the complexity of things, really try to get a program together that you have reasonable confidence is going to work before you come to class. That's probably the only advice that I could offer. Again, it's because I'm not sure exactly where the difficulty is. That's about as good advice that I can offer. I asked them the GTAs, and they just kind of nodded their heads, and they said, it's just life. This is the way it goes. All right, so what is due this week? There's no memo due this week, but at the end of lab, you will have, you'll submit your notebook. This is the first time that the notebook will actually be graded. Okay, so it's going to be graded this week. You'll get a grade for it. If you want to know what is the rubric, what is the criteria for grading, then go back to number 5 here. Click on that. You'll be sent to a page which has all the backup material for this, like the presentation today, the assignments, and also the grading rubric and the criteria for the notebooks. Okay, let me pause there and ask if you all have any questions. If not, let's dive into the keypad controller. So this is the first slide, matrix keypad interface using parallel I/O. So this is, we're going to interface to a real device, a keypad. We use parallel I/O, which we've done before. Basically, we're going to control, that means basically we're going to send signals to the device. And then we're also going to access information from that device. In this case, it's the keypad. And we are going to use interrupt-driven I/O. Okay, so again, these are all things that we've seen before, but we've got to kind of integrate it to get it to all work appropriately. So this is the device that we're working with. It's a 16 button or 16 key matrix keypad. We basically want to know when one of the buttons has been mashed. And so you can say, well, I know how to monitor a switch. We've done that for several weeks now. But I don't want to use a line for every one of my switches. If I got 16 switches, I would need 16 I/O lines. It turns out there's a way to do this in a more compact way by using a matrix. And so we're going to have to deal with basically looking at several lines of information simultaneously. And that's probably why we have some challenges this week. Okay? So this is the physical photograph of it over here on the far left. And at the bottom of it, it's kind of hard to see in the picture, there's a row of pins. And those row of pins connect to a ribbon cable. This is a sketch of the ribbon cable that has on one edge a red stripe. And then these are the pins that correspond to these. And then the pins correspond to rows and columns of this keypad. And so there are 4 rows and 4 columns. There's a total of 8 pins. And the schematic diagram looks something like this. Let's take a look at it. So we have a matrix of 16 switches arranged in 4 rows and 4 columns, like this. Now this is a totally passive device. There's nothing stored in it. There's no active elements. And so in order to find out what's going on with the device, we basically have to send information to it. We've got to write to it and then see how it returns information to us. And so you see here that the pins are labeled. Here pins 1 through 4 are the columns, and pins 5, 6, 7, 8 are the rows. And each of these things represents a switch. And right now in this picture, all the switches are open. And what happens is that when somebody presses on a button, it basically causes one of the rows to be connected to one of the columns. We get a short between a row and a column. Okay, so normally all the switches are open, and so pressing a contact shorts it. And if we were to zoom in onto one of these buttons, that's what this picture is trying to show. It says normally things are open like this. A column and a row are open, but when you press the button, the row and the column are shorted together. Now, the idea that we have this week is that what we're going to do is we're going to say maybe what I want to do is I want to read the row values. Okay, I want to read each of the rows and see if any of them are have some sort of information that I want. So what we do here is when it's open, nothing is being written to any of the columns. And so what is done is that a pull-up resistor is attached to each row. So by default, what will happen is this resistor, there's no current flowing through this resistor, and so there is no voltage drop across that resistor. So the default voltage on the row is a high voltage. Now, once we press the button down, then the column and that row are then shorted together. And so if we have some other value, some other state on the column, then that state now will appear to the row, on the row. So normally right here, maybe suppose I wrote a 0 right here, then what is going to appear out here on the row is going to be a 0. Even before the button is pressed, the row here is going to be 1 because of this pull-up. This is a pull-up resistor. Okay. But if I write a 0 here, then what appears here on the row is going to be a 0. If I write a 1 here, then it doesn't change anything. I can't distinguish between whether or not the button's been pressed or not. Okay, let me ask you if there's any questions about the role of the pull-up resistor. It basically gives a default data value to the row. But that value will change when I press the button if some other value has been written to the column. Okay.
I have a question.
Yes, question.
Okay, so like when the button comes back up, will it reset to 1?
Okay, so the question is what happens when I let go of the button? Well, when I let go of the button, then the row and the column are no longer connected. And so if the column, say, is equal to 0, then the row gets pulled back to 1. So now the resistor is what's going to determine what the value is. Okay? Good question. Okay, so, all right, so this is one way we can solve our problem. We have a matrix of switches and rows. Okay. So one way to do this is that what we'll do is we're going to treat these as outputs from the microcontroller. So we're going to send information here. We're going to write a pattern of data here. So maybe what I'll do is I will say, write a 0, 1, 1, 1. That puts a 1 here, a 1 here, a 1 here, and a 0 here. Okay. Then what we can do is we can test and see if any of these rows are shorted to that column. Okay, so that's what this scan algorithm description is. It says drive one column low and all the other columns high. I want to see if anything's connected to this column. So the way I do it is I put a 0 here and then see if any of the switches are tied. Now the only switches that could be tied to that column would be switches A, B, C, and D. Okay. So I read then and test the states of the rows. If a row is shorted, that means, or a button is pressed, it will be shorted to that column. And if the row is high, then either it's not pressed, it's not shorted, or it's connected to a column that's already been driven high. On the other hand, if there is a column that's driven low, you're going to get a low output here. All right? So then we'll test to see if buttons A, B, C, or D are connected here. That doesn't test any of the other buttons. The next thing we do is we say, this is not the pattern we do. We'll do 1, 0, 1, 1. That puts a 0 on this column. And now I test to see if any buttons are connected to this column or shorted to this column. So that means either a 3, a 6, or 9, or a pound sign could be connected. If I detect one of these is a 0. And so this is the scan algorithm. I go 0, 1, 1, 1, 1, then 1, 0, 1, 1, and then I go 1, 1, 0, 1, and then I go 1, 1, 1, 0. This is the pattern that I write repeatedly over and over again, basically taking turns driving the different columns low. And if perchance one of the buttons is matched down, then eventually I'll be able to detect that, oh, this line here has changed from its normal state of 1 to a 0. Okay. So this next slide shows that example. Let's see if we do this. This is a case of driving the second column low, leave all the others high. I'm testing to see if anything is connected, is shorted, if a button on column 2 has been pressed. If a button on column 2 has been pressed, in this case the 5 button, then this row, pin 6, I should be able to see a 0. All the other rows will be high. Let's take a look at, for example, at row 1. None of the buttons are pressed. So if none of the buttons are pressed, then what will be the value of this row? Well, this row has been tied with resistors, pull-up resistors, to plus 3 volts. And so since nothing has been shorted, then the default value for pin 5, row 1, is a high, a 1. See a 1 right there. This second row, row 2, is also tied with pull-up resistors. Normally, it would also be pulled up to 3 volts. But because somebody has written a 0 here to this column, and I've shorted it now, then this 0 finds its way, propagates its way, follow the blue lines, and it follows out here, and this 1 turns into a 0. Rows 3 and row 4 behave like row 1. They have no switches closed, and so their default values are the values determined by the pull-up resistors. Now you can definitely see that there could be other flavors, variations on a theme. You could say maybe what I want to do is I want to write, I can pull everything down so that and the normal values would be all 0s. And then I want to see if any one of these is pulled high, but then rather than putting a 1, 1, 0, 1, I want to do maybe just the opposite of this. Maybe I want to write a 1 to a particular row and leave all the others, column, I'm sorry, write a 1 to a particular column and leave all the rest of them as zeros. Here we're showing a case of using 0 as the signal that we want to detect. Now the reason we do that in this particular case is because the interrupt that we're going to use this week is active low. So when something goes low, we say, oh, there's an interrupt. Okay. There's other ways to do this. You can do it without scanning. What we could do is we could start off and say, let's write zeros to all the columns. Write zeros to all the columns. And so if a button is pressed, then I immediately will detect, hey, there's something on this row that has been shorted to a column. But I don't know which column because I've written zeros to all the columns. But at least I have identified, oh, there's something on this row has gone low. Now let's reverse things, and now let's write zeros to all the rows. And the button is still pressed, and now I read the columns. Notice that the pull-up resistors are now on the columns. Down here, the pull-up resistors are on the rows. And now I read it, and I write zeros to all the rows. And since this button is now masked, then this column shows up with a 0. So now I know that the answer is, oh, it is the button on row 2 and column 2. And I could make a little lookup table. No scanning involved. A little bit more complicated, however, because now what used to be an output pin has to become an input pin. And what was an input pin now has to be an output pin. So that means I had to change the setup of my port and do this quickly. Okay? So more than one way to skin a cat. Some issues you may need to be aware of. There is a slight delay from the time you, on your code in your program, said writes to the port. My pattern, 1101. There's a slight delay from the time you execute that instruction to the time it actually kind of goes through all the hardware, all the buffers internally, and finally appears at the external pins. And so you might need something like this. You write to the output port, and then for a few steps, do nothing. Just increment a counter for a few dummy loops. And that gives a little bit of time for the information to get out to the port. Okay. I talked about the pull-up resistors. They can be pull-up or they can be pull down. These resistors do not have to be physical resistors. It turns out that the port, the GPIOs, the general purpose I/O ports, have a configuration register, PUPDR, pull up, pull down register. And you can decide whether it's going to be a pull up or whether it's going to be a pull down or nothing. Okay, so you write to 2 bits. 0, 0 means nothing is connected. 0, 1 means this is connected. And 1, 0 means this is connected. And so the example, if I want to activate a pull-up resistor, here's the C code. So GPIO, I want to go up to the pull-up, pull-down register, and I got to clear and set the correct bits. The bits correspond to the particular port. So every port line, here's line 0, line 1, line 2, line 3, has 2 bits. So you pick which lines you're going to use, and then you got to set and clear the corresponding pins. All right, and the other thing we want to do is we have a lot of, we want to do this in an interrupt-driven manner. So what happens is we're going to, as an example, go back here. We said what we're going to do is we're going to write a pattern out to the column and then read the rows in this example. You could reverse it if you want to. And then I'm going to go to the next column, and then the next column, and the next column. I'm going to repeat this. And what I want to do is just continue doing this, and it would be nice if I didn't have to test every single pin to see if there was a response here. So what I'm going to do is just, initially what I'm going to do is going to write all zeros, let's initially just write all zeros. And then I'll just sit here and wait for something to happen here. Okay, so this kind of, it borrows from the non-scan method, the idea that if we write all zeros here, then I can just sit here and wait until something happens. But the 0 could come from any one of these rows. I don't know which one is going to be pressed. Here, button 5 is pressed, but maybe somebody decides to press a different button. So what I would like is for this keypad basically to say, hey, one of the rows went low. Let's interrupt the system and tell it to go into its algorithm, whether it's a scanning algorithm or non-scanning algorithm. And so the way to solve that problem is to take all the rows and let's flag an interrupt when one of them goes low. So let's take a look at this. We have 4 rows, rows A, B, C, D. I want to flag an interrupt when A goes low, or B goes low, or C goes low, or D goes low. And I use De Morgan's law, and that's basically saying, oh, I need an AND gate. Okay? An AND gate says if any one of the lines goes low, I'm going to get a low going out. And so this is the interrupt request line. It's active low. This is a funny symbol for an AND gate. Okay? It's really reflecting this thing. In English, we would say, I want you to flag me an interrupt when A goes low, or B goes low, or C goes low, or D goes low. Oh, and by the way, this is an active low interrupt, which is why we have that up here again. You apply De Morgan's law and we get this. So if I drew an AND gate like this is totally equivalent to this, but it doesn't express this logic in quite the same way. Again, these pull-up resistors, they're internal to the microcontroller. So here's the microcontroller, here's the outside world. These should be configured internally. Okay. Some of you have detected this issue already. I've seen it in some of your logic analyzer slides over the weekend, is that when you mash a button, you don't get a clean 1 to 0, 0 to 1 transition. We call this bouncing. Okay. So what you may want to do is, you're going to see here, you get a 0 to 1 transition, and that triggers an interrupt. But in the meantime, you come and you start working, and you get another transition and another transition. But it was really only one press, and so you don't want to be thinking, oh, I've got multiple presses. And so this can mess up your program. So one of the things you have to deal with is, hey, we need to shut off the interrupt request for a period of time, delay it, and then see if it's still there. Come back. Now, what does the switch box really look like? This is a picture using an oscilloscope, looking at one of the switches. Okay? And so here, it looks like the 0 to 1 transition looks pretty clean, but when you're releasing it, you get interrupt, 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 interrupt. Okay, so looks like you may need a little bit delay. You need to think about where I may need some delay so that I can get past this problem. Okay. Here's another one. Not all keypads look the same. Okay, so there was a button press earlier in time over here. Nice clean rise. Okay. The contacts aren't super clean, and so the voltages aren't always so great. Hopefully, the threshold is right about here, and okay, anything above this is considered a 1. Anything below this is considered a 0. But you can see where there could be multiple times where you're going to get what you think is an interrupt. So this is what we're requested to do. We're going to use multiple ports this week. So use port B to go to the keypad. Use some of them for the rows, some of them for the columns. This is one way to do it. You don't have to do it this way. You may choose to say, I want to use this, and I want to use this sometimes as rows and sometimes as columns, because I don't want to do scanning. But if you want to do scanning, one way to do it is to assign these as rows, which you read, and assign these as columns, which you write. Or you can reverse it and say, I want to read these and write to those. Okay? We suggest that you use port C, use 4 bits as LEDs. Use port A1 as your interrupt request. And what we want to do is we want to ideally be able to determine which button is pressed. So again, there's no new concept here this week, but it will be helpful to review several concepts that we see from past weeks, try to figure out how do I integrate all those different ideas into something which allows me to control, we call it controlling the keypad. Okay? So we've seen these ideas before. How do I read and write to I/O ports? How do we clear bits? Because we've got to configure them. Configure ports. How do I get an I/O line to interrupt the CPU? We did that all in weeks prior. Okay? So write up a program that does initialization of the ports. And then again, there's the counters again. 1, 2, 3, 4, 5, it's still counting. We don't have multiple counters this week, so it's a little bit easier. But now what happens is, if a button is pressed on the keypad, figure out what button it is, and then rather than displaying the count value, display the button value, and do it for about 5 seconds. After the 5 seconds are up, go back to displaying the count value. And hopefully the counter has been running in the background, because this is interrupt driven, and the interrupt is simply just saying, okay, what button was pressed and what value should you be displaying? Should I display the count or should I display the button press? Okay. The purpose of the interrupt handler is to say which button was pressed and then tell the system to display the button number or the key number on my LEDs. I have to deal with the debouncing that we're talking about. Okay. If you're doing some debugging with a logic analyzer, this is something that you might see. Okay. So let me explain what's happening here. The top line here is the interrupt request line. So if you see something go that low, that means there's an interrupt. Okay. Now then what we have here is we have the 4 columns and then we have the 4 rows. So right now, in this particular case, these are driven from the microcontroller, and these are now rows. These are inputs to the microcontroller. So think of this as, if this is the boundary of where the microcontroller is, this is information being written to the columns, and now we're reading the states of the rows. So this is outputs, inputs. So what has happened here is, you notice initially, let me zoom in a little bit, the columns are written, right now, they're written as 0, 0, 0, 0. Somebody mashes the button in row 1, and that's why the rows right now are 1, 1, 1, and then this is a 0, because it got shorted to one of the columns. So now I know it, well, I haven't read it yet, but this creates the interrupt. One of the rows goes low. One of the rows goes low. These are all ANDed together. All 4 of them are ANDed together. And so since one of the rows has gone low, it's going to produce an interrupt request. So I go from the columns being 0, 0, 0, 0. Now I've got to start scanning. Which column is it? So the first thing I do is I say, well, let's try, see if it's this column. I'll put a 0 here, and a 1 here, and a 1 here, and a 1 here. So I'm going to test just this column, column 1. Well, I read the rows, and they're all high. This is a 1, 1, 1, 1. So therefore, there was nothing in that row touching that column. Now I go to the next column. Now what I do is I put a 1 here, a 0 here, a 1 here, and a 1 here. And lo and behold, the row here goes low again. Okay. It goes low again, and so now I'm in column 2, row 1, so I know what button it is. Notice that the interrupt request will go low again. Why? Because I've always ANDed my 4 rows. And so this looks like another interrupt request. But we don't want to be fooled in thinking this is another interrupt request. So the routine, the interrupt service routine, needs to be like, look, I'm busy right now processing this interrupt. Don't interrupt me again. So you got to go through this process of enabling interrupts, detecting the interrupts, but oh, by the way, now I've got to interrupt. Don't look at anything more again, because I don't want to be fooled by this edge again. All right, you understand that? In this particular piece of software, you notice what he does next is after he's tested that row and column and discovered, oh, I got a row here, he still continues on and says, well, let me try writing a 1 here, a 1 here, and now a 0 here, and a 1 here, and test and see if anything is connected to that column. You could argue, I don't need to do that. I could write my program to say, once I've detected which row has been activated, I could just skip this. But he wrote his program to still test column 3, and then finally test this last column, column 4. And you see, and then in each of these cases, the rows always stay high, because no button in those columns were pressed. And so, since there were no buttons in those columns pressed, the rows float up high because of the pull-up resistors. Okay? So this is a situation where the answer is the button is in column 1, row 2. Column 1, row 2 is probably the, let's see, what button is that? Column 1, row 2 is probably the 4 button. All right, so that's the goal this week. Any questions? Okay. Again, I want to encourage you to say, conceptually, there's nothing difficult here, but there's a lot of data flying around, and so you may be a little bit frustrated trying to figure things out. And probably, if you're not real sure about the interrupts, that may frustrate you for another week or so. Everybody understand what's due this week as far as submissions go? No memos, but submit your notebook. All right, that's all